tutorial lectures. And today he's going to tell us about introduction to DMRG.
Thank you very much, and welcome to the second talk. So what I'm going to be talking about is PMRG, and before that, I just want to tell you, I gave an introduction to many body techniques, and there are many problems with the restricted CID is not size consistent, is an uncontrolled approximation, and coupled cluster techniques are size consistent but good only for smaller systems. ED again possible only for smaller systems as their Hilbert space dimension grows exponentially with system size, and extrapolation to infinity thermodynamic limit is basically something that does not have a theoretical basis by itself. And then quantum Monte Carlo methods are better suited for high dimensional lattices because you have the techniques which are much better for low dimensional lattices that I'm going to discuss. And also QMC for fermions and frustrated spin problems suffers from sign problem. Okay, let me talk about renormalization method. In general, what renormalization means is that given a Hamiltonian of a small system, you change the size of the system to a larger system, the coupling constants get renormalized, but the size of the matrix that is going to represent it does not change. In other words, you can also look at it reverse way. That is, you have a large system, being given a Hamiltonian for the large system. You go to smaller and smaller systems, the size of the Hamiltonian matrix does not change, but only the matrix elements or the coupling constant change. So that is the what we mean by renormalization. In basically a method like DMRG, it involves changing matrix elements systematically without changing the dimensionality of the matrix. So if the dimension of the matrix is like a million by million, it will continue to be a million by million even if you deal with a 20-side fermionic problem or 24-side fermionic problem or so on and so forth. So, and the numerical renormalization group was first introduced by Kenneth Wilson in the context of the Anderson impurity problem, not the Kondo problem, Anderson impurity problem. And Wilson's numerical renormalization for the Anderson impurity problem was the following. What he did was he took the conduction band and he replaced the conduction band by a set of orbitals corresponding to a set of energy levels within the band for each orbital. And the energy was divided in the conduction band on a logarithmic scale. I'll show you a picture about that one. And at each energy value, you have an orbital with a constructive superposition of the band orbitals in the energy range introduced. So I'll show you what I mean by that. So here I have the band, okay, and here I have the impurity. The impurity is interacting with the band, and the band energy is changed. Is partitioned or made into intervals with logarithmic scaling. Lambda is the scale factor, and lambda equal to 2 means you are having the division of the band into 1/2, 1/4, 1/8, and so on and so forth. And corresponding to each one of those energy scales, you have a single orbital, which is these blank ones of the orbitals, and then you have the impurity here, and impurity has a Hubbard correlation, and what you are going to do is introduce the impurity and the first orbital to the calculation for the energies and the ideal states, and keep only a few low-lying states and replace them by another effective Hamiltonian H1, and introduce a second impurity which has an energy epsilon1 and a transfer integral T0, and you do the calculation for this one. And again, from these two, you get a Hamiltonian H2, introduce another orbital at energy E2, and you have a new transfer integral T1 and so forth. And of course, the transfer integrals die down as lambda into the minus n by 2. And this was the one that was used first by. Yeah.
Do you have spin degrees of freedom here?
Yeah.
Okay.
Both spin and charge degrees of freedom, because the impurity is an Anderson impurity, and it has got a Hubbard parameter for the Anderson impurity and a site energy for that. And for the other orbitals, it's only no interaction. And there's a hybridization term between the orbital that I put here and the effective. So this was the first one. They wanted to extend it to simple systems, like for example, the spin chain, Heisenberg spin chain, Chewy and Drake tried it, for example. And what they found was when they keep the lower-lying states of the spectrum and then construct a effective Hamiltonian and keep adding spins, the energies were off by about 10%. And 10% is too large. 5 to 10% was the error, so it failed. And White found out the reason for that. He said that supposing you look at a particle in a box. So you have a box of length L by 2. You put two boxes together and construct a box of length L. And you take the ground state of that one to construct the ground state of the box of length L. What you are going to get is the first state, because you can never avoid getting a node in the middle. So if you get a node in the middle, it means that you are going to be having an excited state, and you can't get the ground state of the particle in a box. You will never converge to this one. So this is an example where which shows why the energy-based quantum renormalization group does not work. Of course, the method of the particle in a box, he was able to correct it by changing the boundary conditions on one side, changing the boundary conditions on the other side, and having open boundary conditions on both sides, and then trying to construct the effective Hamiltonian using the eigenstates of these systems. But you cannot do that in a extended interacting system. So he introduced a different method. So it's called the density matrix renormalization group method, and they introduced in 92. And what he did was he will iteratively build a large system starting from a small system. You have a large system, say for example, a system of about 4 sides or 6 sides, and then you obtain the ground state of the 4 or 6 side system and construct the density matrix for one of the part of the system, like the left block, which is 3 sides, and the right block, which is 3 sides. And when you get the part of the density matrix for that one, now you diagonalize the density matrix and keep only a few of the states with the dominant density. Okay. So, for example, if you have a 3 side on the left side and 3 side on the right side, the density matrix will be 8 by 8 density matrix. If it is a spin problem, or it will be a 64 by 64 density matrix, because every side has either degree 2 or 4, depending upon whether you are dealing with a spin or a fermionic problem. And from the 64, you will just keep something like 32 states with the highest density. And then you take those eigenstates of the density matrix and renormalize your Hamiltonian of the 3 particle system on the left using that. I'll come to all those things in a while, but I'm just telling you how it is done. And incidentally, I want to tell you that the idea of using density matrices for doing correlation energy calculations is not new. Chemists were using 1 particle density matrices, and the eigenstates of 1 particle density matrices were called natural orbitals, and they used to construct Slater determinants using natural orbitals and try to calculate the correlation energy, and they found the correlation energy converge very fast if they use natural orbitals as opposed to the real orbitals. But here the difference is that these are not just orbitals of 1 particle state, these are many particle states, because these are many particle density matrix that you have constructed, and these many particle density states are the ones that become the basis states for the system blocks. Okay. So here I have how one implements it so that you know, you will know exactly how it's done. Let us start with a four-side problem. I've taken a spin problem just for the sake of simplicity. So the Hamiltonian is S1 dot S2, S2 dot S2 prime, S2 prime dot S1 prime. I have called primes as the ones on the right side and unprimed sides as the ones on the left side. On the left side, you will have the four Fox states, which are spins down, down, spins up, 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 down, down. They are the four Fox states. And you can get the eigenstate of this Hamiltonian H, which is the psi 4 0, 0 representing the ground state, and 4 is the size of the system. And this can be written, re-expressed as a product of the states on the left with the states on the right. It's a direct product of the states on the left to the states on the right, and you have the coefficients here. And the summation runs over Fox space dimensions of both left and right. So sum over L, sum over R, CLR, L times R. Now in the renormalization procedure, you have to construct the density matrix. How do you construct the density matrix? The density matrix for the left part corresponding to matrix element L and L prime. You know, supposing I have, for example, I want to find out the density matrix element between this state and this state. Okay, you can take L and L prime. Then all you do is sum over the right part, the CLR, CL prime R, and then you get rho 2 LL prime. And if you diagonalize it, then you get rho 2 0, mu 2 will give me ML mu 2 ML. Okay, so L is the index of the eigenstate. Now, what you do is you take these mu 2s and construct a renormalization matrix, which is basically an L by M matrix, because if the dimensionality of the density matrix is L by L, you just take M of those eigenvectors which have the largest density, treat those M vectors as the column vectors. So you have a O to 0, which is actually L rows and M columns. It is an L by M matrix, and M is less than that. So you have got a density matrix, which the renormalization matrix. Now what you do is the following. Construct do the same thing on the right block if there is no reflection symmetry. If there is a reflection symmetry, you don't have. Then you construct the Hamiltonian H2 of the left block. Okay, I'm talking only about the left block. So you can construct it explicitly. Okay, and you do the renormalization of that using O2, H2, O2 diagram. Okay, so you see that H2 is a L by L matrix because it is the full Fox space dimensionality of the two sides. So it's the L by L matrix, and O2 is a M by L matrix, and O2 dagger is a L by M matrix. So what you will get is a M by M matrix, is actually a renormalized matrix of the left block. You can do the same thing for the right block, renormalize the right block. And after you renormalize the left and the right blocks, you can set up the matrices for operators, like the spin operators. Okay, so for example, S1Z, you can set it up. Okay, if you set up for S1Z, let me go back. I will show you how it will look like. So if you set up for the S1Z, you will have, for example, minus half, 3 zeros after that, 0 plus half, 3 zeros after that, and then 0, 0 plus half, minus half, 2 zeros after that, and then 3 zeros plus half and 0. So because all that you have done is expanded, inflated your dimensionality, and then you have written down your this matrix in the Fox space L instead of just a single side. Okay, after you do that, you renormalize the spin matrices as well. So once you renormalize the spin matrices and you do it on the right block also, then what you do is you add two sides in the middle. Okay, if you add two sides in the middle, you can write on the total Hamiltonian now approximately as the renormalized left part, the renormalized right part, and the new spin S3 and S3 prime, they are interacting. And then the renormalized spin 2 on the left part is interacting with S3. And the renormalized this is S2 prime is interacting with S3 prime. So these are the interactions that you are having, which involves the renormalized. Okay. Once you write it down, what you can do next is you can write on the Hamiltonian matrix elements in the fixed density matrix eigenvalue and Fox space space. Okay, so the basis is the following. The basis is the density matrix eigenvector of the left, direct product to the Fox space state of spin 3 primes, Fox space state sigma prime, and then the density matrix eigenvector of the on the right. So you have the basis mu2 sigma 3 prime mu2 prime, and you want to find out the matrix element with the general mu2 tau 3 prime mu2 prime.
Yeah. Maybe I have missed, but how did you renormalize your spins? On
Spin.
the left hand? Could you go back to the previous
sure.
page? I'm asking what the S2 and S2 prime.
Okay, so just as H2,
So you were saying
I have S2. I can write down the spin operator for the second for each spin on the left hand side. For example, if I write down the spin on the left hand side, the matrix is see if I have this, the basis is, let's say this one. And the matrix will for the spin on the for this spin, which I call spin 1. Okay, so this will be half, then 0. So it's a 4x4 block that I have. This I can renormalize by using
O2, right? O sub 2.
O sub 2. Okay, so that's how we did it. I renormalize.
Okay, yeah, thank you.
So once I get the Hamiltonian matrix, I can get the lowest eigenvalues, right, of the 6-side problem. And from the 6-side problem, I can construct the density matrix of the 3-side problem just by tracing out on the right side state mu2 prime and sigma 3 prime. And once I get the left density matrix, I can get the density matrix eigenvectors, and I can have the renormalization operator O for the 3 sides, and continue this. Add 2 more sides and continue the iteration until you get the desired side. Okay, any questions? This is the most basic numerical. I mean,
So can you go 2 slides back? I mean,
to previous slide.
yeah, when you introduced the 2-side problem where 1 prime and 1 2. Yeah, before that.
Yeah. So I mean, I'm
when
not,
you constructed the density, so where rho 2 is LL prime.
Yeah.
So and after that you wrote O is equal to the last line.
Yeah.
So I missed. I mean.
so the thing is that usually when it's only a 2-side problem, there is no truncation because it is a 4x4 matrix. You don't want to have a 2x2 matrix. So you only start truncating when the density matrix order becomes large enough. Okay. For example, when you have like 8 spins or something like that. Okay. Then the density matrix on the left side is like 2 to the power 8 by 2 to the power 8. Then you will truncate. You don't truncate it before.
So I'm unable to understand the mathematics of it.
Well, mathematics of it is very simple. You see, the point is that you have m columns in the matrix. The m columns corresponding to the m eigenvectors. Okay, and L rows. Okay, so L rows and m columns is what you have, and you take that is a renormalized matrix O, and the Hamiltonian matrix and the density matrix is L by L. Okay, you take O dagger, density matrix and O, in which case you have a m by L multiplying into an L by L matrix, multiplying into another L by M matrix. So what you will get is a m by L. Okay, so because the renormalization matrix is not a square matrix, it's a rectangular matrix.
And what about mu index, mu Q?
Mu index is the mu's are the eigenvectors of the density matrix. So mu is actually L vector. It has got L components. The vector mu has L components corresponding to the L basis function of the Fock space in the vector. Okay. Any other question? Yeah, please.
So let me confirm the situation. So we need to pick up the largest eigenvalues.
Correct. Yeah.
Okay. So we pick up the M largest.
M largest, M dominant eigenvalues of the density.
Thank you very much.
Sir, also this density matrix, the first density matrix is in the full Fock space.
Yeah, because you don't truncate it, because you know what's happening is it's too small to truncate. You can do the calculations. Exactly. It will only become a change of basis. Change of basis from the raw Fock space to the density matrix, and you don't truncate. Now,
When we are actually choosing the density that contributes largest, so we are making an approximation there.
correct.
So we are truncating the what you are
That's right. On the basis of the eigenvalues of the density matrix, you truncate,
we're choosing those who has largest.
which have the largest densities.
Any other questions?
Okay.
So this is just comments. Diagonalizing the density matrix is a very fast step. Even if the density matrix is like 1000 by 1000 or 2000 by 2000, you can actually sector them. Is block diagonal in both the number of particles and in the spin Sn, let us say. Okay. So because of that, each block can be diagonalized separately. So that's a very fast step, and is mainly applicable to one-dimensional systems which are away from criticality. Okay, which is if you have a zero gap, then you have a problem. That's because if you define the entanglement entropy as the entropy of if rho alpha are the eigenvalues of the density matrix, then you can define the entanglement entropy as sum over all the eigenstates minus of rho alpha log rho alpha to the base 2. Base 2 is usually chosen for whatever reason. And in gap systems, what is known is that this entropy scales as the area between the system and the surroundings. Okay. So in the case of a one-dimensional system, the area between the system and the surroundings is always constant because you only have one side. So because of that, the entanglement entropy does not change when you keep increasing the size of the system in one-dimensional cases. But in two-dimensional cases, it keeps changing. Okay, because the area keeps changing as you keep increasing the system size and compared to the environment. So because of that, what happens is that it has been shown that for a given accuracy, the number of density matrix eigenvectors you have to retain, which is m, goes as exponential of s. Okay, it's proportional to the exponential of s. Okay, and if s is a constant, independent of the system size, you will have the same accuracy for a fixed n. So you can do the calculations for larger and larger systems without increasing the number of density matrix eigenvectors you have to retain. So that is one of the major advantages of one-dimensional systems. So that's what I said. M goes as exponential a before exponential as, and in gapless one-dimensional systems, this is what happens. And actually, there are lots of organic molecules which are polymeric in nature and conjugated molecules, and which are very important. For example, if you look at your cell phone, then the light-emitting diode there is nothing but an organic polymer. So if you want to do calculations for such systems, then density matrix renormalization group is probably the best method. And I will not say more about it. So that's how we started doing density matrix renormalization group, because we were interested in the electronic states of organic polymers. And another thing is that these are all sparse matrices. The number of matrix elements are very few. Okay, the number of non-zero matrix elements, well, not as sparse as, for example, the exact calculations, but nonetheless they are sparse. So you only store, do arithmetic with non-zero matrix elements, because with the zero elements, multiplication by of any element by zero is zero, and addition does not change the element. So you only have to do arithmetic with non-zero matrix elements, and all you need to do is store the row and column index and value of the element. There are ways of storing it. It can be very compact. I'm not going to talk about it much. And there are very many different ways of storing it. I have just mentioned here because I will leave the transparencies behind, and also you have the videos. You can look at it and then find out what the details are, how to store it. Okay. So all it requires is to store the row and the column index of the matrix element and the value of matrix element. In general, you only require 164-bit integer. That's it. Nothing more than that. You can do it almost. It scales as number of non-zero elements. Then now I'll come to how do you solve the eigenvalue problem, because this is one of the most important things, and there are many different techniques to solve it. Quantum chemists in the 50s and 60s used what was called the Nesbett algorithm. It's also called the coordinate relaxation algorithm. In a coordinate relaxation algorithm, what you have to do is you have to solve the eigenvalue problem, which is C is equal to rho C. Okay, H is a Hamiltonian matrix, C is a vector, rho is the eigenvalue, and C is again the vector. So H is equal to rho C. So I can write down here the ith equation. Okay, so the ith equation is what? I have separately written the ith element, the diagonal element. It's just Hij Ck plus Hii Ci k minus 1, and then I'll tell you what this alpha I k is, and the one with the higher column numbers is equal to rho k minus 1 Ci k minus 1 plus alpha I k. So I'll tell you a little more about this. So the first thing is the following. That is, I've written the ith equation. If you just take the left-hand side without the alpha I k, okay, then the left-hand side and right-hand side are not identical. Okay, because you have not solved the problem. When alpha I k is 0, the left-hand side is not equal to the right-hand side. So what you want to do is you at least the ith equation you want to solve correctly, which means what? I will change the matrix, the component which is Ci k minus 1 at the k minus 1 iteration by adding something which is alpha I k. Okay, such that the alpha I k is so chosen so that the left-hand side is equal to the right-hand side. Okay, so it's very simple. Look at the ith equation. If you have a random vector that you have chosen as the eigenvector and it is not really an eigenvector, the left-hand side is not equal to the right-hand side. So you want to make the left-hand side equal to right-hand side. So what you do is you take the ith equation, change the I matrix, the ith component of the vector by adding some alpha I, and ensure that left-hand side and right-hand side are equal. So which means that alpha I k is given by this amount. Okay, I've just taken this onto the right-hand side and alpha I k to the left, and I've shown it. So this is nothing but what you might call the kind of similar to a residue vector, ith component divided by HIL minus rho k minus 1. And one full iteration is when you go through changing all the components one time. Okay, once. The problem is that this is a very stable method, but a very slow method. Okay, this Nesbett algorithm is stable but very slow. And then you have other methods. The other method is a Lang-Chose method, which was spoken by in yesterday's talks. And you start with an n component trial vector. So A is a n by n matrix. So what you do is you take the n component vector, operate on that vector by the matrix A. You can decompose the result AB1 into something that is along B1, which is A11 B1, plus something that is in the orthogonal direction A1 to B2. B1 comma B2 is equal to 0, but B2 comma B2 is equal to 1. Okay, so what you have done is you have basically decomposed AB1 into a vector which is this is a vector which is along the direction of the chosen vector and another one which is along the orthogonal direction. Now you take this B2 operated by A. That will be A21 B1. Okay, I can express it as a linear combination of A21 B1, A2 to B2, and the remainder is A23 B3. I make it such that B1 B3 is 0 and B2 B3 is 0, which means I'm just doing a gram split orthonormalization of the vector A B2 to B1 and B2 to get the vector B. So B3 is AB2 minus of AB2 comma B1 B1 minus of AB2 B2 comma B2, where AB2 B2 and AB2 B1 are the inner products. Similarly, I can come all the way down to here, and when R is large enough, then I can look at this R by R matrix, okay, which is what I get, and then I can get the eigenvalue of that one. Okay, that's a small matrix representation of the large matrix. So that's what the scheme is. This method is not very stable, but converges very fast. Okay, and if A is a Hermitian matrix, it's easy to show that the matrix, the Lanchos matrix, the small matrix that you get the R by R, is a tridiagonal matrix, because you know that in the Hermitian matrix, the one that is the transpose is Aij is equal to Aj bar. Okay, so that's why we can show that it's actually a tridiagonal matrix. And so this I've just shown you the proof of that. I don't want to go into the proof, it's quite simple. Now, so we have two methods. One is, yeah.
I have a question about the instability of the Lanchos method. So when the Lanchos method becomes unstable?
When the Lanchos method
Becomes unstable.
unstable, when the eigenvalues are close, the low-lying eigenvalues are close, and in general, it's supposed to be unstable. So people don't use Lanchos method as much as what I'm going to talk about, the Davis method.
Okay.
Okay.
So
But it is unstable when the eigenvalues are close, just because it is very similar to the power method. So in the power method, what happens is that you take a vector, keep on applying the operator on that one. So when two eigenvalues are close, you see that the one that is smaller doesn't go to 0 very fast, right? Because the ratio of the eigenvalues is very close to 1. So you have to raise it to several powers in order for that to be going to 0. Okay.
okay.
So that's why when the two eigenvalues are close, Lanchos method also doesn't work very well. It's like the power method.
Okay. So but it means that just the convergence speed becomes slower.
Yeah.
So does it mean the unstable?
Oh, unstable means when you stop before that, then it will be, the extent of mixture of the lower and the higher eigenvalues. The eigenstate may be unpredictable. So for that reason.
Okay. Thank you very much.
In degenerate case, we have a problem. Even when they are close, it's difficult. What's it? Yeah.
There's a question.
Can ask them to unmute and ask them.
So any questions?
Hello. Hello.
Just unmute yourself and ask, directly. No?
Prabhakar, you unmute.
Hello.
Prabhakar, unmute yourself and ask a question.
I'm audible. Hello.
Yeah.
So my question is, so you are saying that if the eigenvalues are very close, we cannot perform Lanchos algorithm. So if the system has degeneracy, how can we deal with this?
How can we?
If the system has degeneracy, let's say, can we use the Lanchos algorithm to calculate the?
No, it's difficult because if it is degenerate, probably it will converge to the lowest eigenvalue because I have not tried it myself, so I cannot tell you very confidently. But usually even for the degenerate cases, we want to get the second degenerate state, then I don't know how you'll get the eigenfunction, because you'll get an eigenfunction, it's a linear combination of the state, degenerate states. So I really don't know how to know that the state is degenerate when there is a Lancho from the Lancho's algorithm.
Okay, okay, thanks.
Okay. Oh, sorry. Yeah, in the Davidson's algorithm, what you will do is you take this n by n matrix, start with a small set of n vectors, b1, b2, bp. Okay, these are all n component vectors when I say n vectors. So you can start with a small number of those. And you can construct a small matrix representation of the large matrix. Okay, so you take the large matrix and form bj transpose abi. That will give you the small matrix element, small ai. And you obtain the eigenvalue of the small matrix. Okay, the lowest eigenvalue you are looking for the lowest eigenvalue. This lowest eigenvalue is just given by xp, which is that just the components of the p by p small matrix here I have. The small matrix eigenvector is cp. So then xp is given by cp1 b1 plus cp2 b2 etc. plus cpp b2. So this is very simple. This is b1 b2 b3 are the n vectors, and the c1 c is a p by p vector, so it got p components, and you can write down your eigenvalue of as eigenfunction as a n vector at the p iteration. So x has got n components in the p iteration, and you have cpp1, cpp2, etc. cpp. Okay. Then now what you do is you construct the residue vector. Okay, the residue vector is nothing but the difference between the a times xp minus cp times x. That is the residue in the eigenvalue eigenvector equation. Left hand side minus the right hand side. So from the residue vector, you take the ith component and you define the ith component of a new vector alpha at p as residue vector r at p. Ith component of the residue vector divided by ei minus the eigenvalue at the p iteration. Okay, which means depending upon the dominance of the eigenvalue, if the diagonal vector, okay, diagonal element, if the diagonal element is close to the eigenvalue, then that component of the eigenvector is becoming important. Okay, so you just compute that. Yeah, you had a question? So then you get the vector alpha. So alpha is a vector because component by component. You can get now the vector bp plus 1. That is augment the space which is p by adding a vector bp plus 1, which is Gram-Schmidt normalization of the vector alpha p to the earlier basis vectors pi and normalize. Okay, now we get the vector bp plus 1. Construct now the new row and new column from the p by p matrix. You augment it to p plus 1 by p plus 1 matrix, just as you do in the Lanchos. No different. Okay. Once you do that, you can get the eigenvalue of this matrix and the eigenvector and continue again this thing iterating. That is, you take that and then get the xp plus 1. From that you get the the residue vector rp plus 1. From that the correction vector alpha p plus 1, and then bp plus 1. So bp plus 2 and so forth. Okay. So that's how you will do it.
You chose.
I chose the lowest eigenvalue.
No, so when you chose the n in the previous one, how large would it be? Like it would be.
The n by n matrix.
Yes, so it's not your whole matrix, right? It's
No, n by n matrix is the whole matrix. It's the large matrix, the Hamiltonian matrix corresponding to
the full
matrix. Your
and you choose
KMRG matrix or
the back ones.
yeah, your exact diagonalization matrix are the KMRG.
Okay. So that.
Should I go back further?
No, this one only. So
N
then-
by n.
And A is some arbitrary matrix or
I'm taking an arbitrary matrix and then showing.
Okay.
Okay. A can be the Hamiltonian
it can be the
matrix
Hamiltonian.
and n can be the either the Hilbert space of the Hamiltonian matrix or the truncated Hilbert spaces. Okay.
And you choose a set of B1 vectors.
You can just start with B1, one vector, and then still get the result. Okay. So the B1 corresponding to the lowest diagonal value, you take that component of the B1 to be 1 and the remaining to be 10 to the minus 2 or 3, and then start your vectors. Okay. And this is extremely good because you can, I mean, I have done it for 1.5 billion by 1.5 billion. So it's extremely good.
So could you go back to the slide where you were? So you are defining AIP.
Which is next slide?
No, the last slide where you were. After, yeah. So AIP, you have defined it like that. So in denominator, you're writing HII minus EP, right?
Here, HII minus EIP. The IM value of the thing.
Why are you choosing it like that? Because if EP is very near to HII, then this will blow up, right?
You also normalize. You take that vector, also normalize it to the previous basis function, and then you normalize the vector. So even all it means is it go up means it will be closer to 1. That's all. The component, the vector component will be closer to that. If HII minus EP is small, okay, then alpha will go up, right? You said it's going to go up. But then you remember, I'm normalizing it. So it comes down to less than 1. Okay, so it's better to use Davidson algorithm because that's converges faster, and depending upon what eigenvalue you actually target, the lowest or the second lowest or the third lowest, you get eigenvalues. All right. Well, you can calculate the evaluation of matrix. You can calculate the properties of a DM from a DMRT eigenstate. So supposing you have got an operator O, okay. So if the operator O that is the spin density operator, and you want a side spin density operator, and if the site is on the left hand side, then you have got a renormalized matrix O mu U corresponding to the operator O, right? Because you can always, for example, if I want to find out the spin density at the site 1, I have S1 Z and I have renormalized it, I have S1 Z tilde. And that has got the matrix, there's a M by M matrix with indices mu and mu. So if I want to calculate that, it's just a trace. Okay. And if I want to calculate correlation function of a site to the left and a site on the right block, I can just extend it and just multiply the two matrices here and then get the correlation function also. But the problem is when two sites are in the same block, because when two sites are in the same block, they are entangled. We have not removed the entanglement. So because of that, you will have to carry those two sites together. You have to obtain a matrix representation of the product of the two operators and keep renormalizing the matrix representation of the product. Okay, it is not sufficient to just multiply the two matrices at the last stage, but instead you multiply the two matrices at every stage, renormalize it, and then carry them through and then calculate the matrix. Okay. And you can also include cyclic boundary conditions. Earlier, cyclic boundary condition in DMRT was a problem. But when we started applying it for molecules, we started building the system from inside out. So here also you can do the same way. So supposing I want to have a calculation for a ring. So if I'm looking at a four-side ring, I start with this is a left block and the right block. Now I expand this 4 side to 6 sides, not by adding, I already have a bond here, right? And a bond here. So now I'll add, it's not an open chain. I started the ring, and then I can add a side there and a side there, and then construct a ring of 6 and do the calculation. And when I want to go to the ring of 8, I'll make this the left block and that the right block and add the 2 sides diagonally. And now I get a left block which is 4 sides and the right block which is also 4 sides. A ring of 8 and ring of 8. Now you can again break it up into 2 4-sided things and go back and add the sites as here. Okay, so it is possible to do DMRG calculations with cyclic boundary conditions, because when Steve White introduced DMRG scheme, he said cyclic boundary conditions are not very good to it's not very accurate for cyclic boundary conditions. So he started putting one side in the middle and one side at the end, so that the side at the end is the one that's interacting with a most renormalized side, which is number 1. Okay, so and that was giving him errors. And in order to avoid the errors, what we are doing is we are putting the sides in the middle only, but we have already started initially with a ring, so that you already have cyclic boundary. So this is the way you can actually implement the cyclic boundary condition. Was there anything else that I just saying here? So I mean, Manoranjan has extended this technique to things like metal axis, and we have also had calculations on other kinds of systems, which are like skewed spin ladders, which are very interesting spin ladder systems. And it is possible for any quasi one-dimensional system to be constructed. So you want to get low-lying excited state, then what you do is you take the eigenstate corresponding to, supposing you want to get the second state, take the eigenstate corresponding to the second state, construct the density matrix from the second eigenstate, and do the whole procedure as before. Then you get, and every time targeting the second state, then you get the second eigenstate, convergence to the second eigenstate. Okay, so that means you start with psi 2 and get the density matrix from psi 2, construct the Hamiltonian from the density matrix eigenvectors, renormalized Hamiltonian, and again from the renormalized Hamiltonian get the second eigenstate, and again construct the density matrix from the second eigenstate and so forth. So you always have to start with second eigenstate. But you know, this is all very well. By working in different MS sectors, you can also get spin excitations. For example, if you work in the MS equal to 0, then most probably you get the singlet state. If the singlet is a ground state, it's the antiferromagnetic interaction. You want to find out the triplet state and the gap to the triplet state, what will the MS equal to 1. Then the lowest state in MS equal to 0 and the lowest state in MS equal to 1 will give you the spin gap if they are not degenerate. If they are degenerate, it means that spin 1 is a ground state. Okay? If spin 1 is a ground state, then the lowest energy in the MS equal to 0 and the lowest energy state in the MS equal to 1 will be degenerate. Okay? Because the triplet degeneracies are there. But you know what happens is many a times we are interested in, particularly in things like conjugated polymers, we are interested in optical gaps. Okay, optical gaps require the charge to be moved from one side to the other, because otherwise it cannot couple to the electric dipole of the light. Okay, if charge has to be coupled to that one, then you are going to be having movement of the charge, means you are going to be having a correlation built in. That is, you are going to put 2 electrons on the same side, so the correlation energy is high, and so the optically excited states usually have higher correlation, and because of that, larger gap. Okay, because the optical gaps are large. The large gaps are because you have put 2 electrons on the same side in the optically excited state. Okay, so and the optically excited state may not be the 4th state, 5th state, or whatever. It may be the 400th state, depending upon the system size. It may be anything, because you know the lowest energy spectrum will correspond to all the covalent states, which means all sites singly occupied minimum. Okay, so if you have n sites, 2 to the power n low energy sites will be there, and then you'll have the optically excited states. So if you want to get that, it's rather difficult unless without using symmetry. So you have to use symmetry. So how do you use symmetry in these cases? The system is bipartite, so you have electron hole symmetry. I think I spoke about electron hole symmetry yesterday. And then if you have a non-relativistic Hamiltonian, total spin is conserved. It also implies spin inversion symmetry. That's in the MS equal to 0 sector. Okay, if you flip all the spins, then the Hamiltonian does not change. Okay, the Hamiltonian remains the same even if you flip all the spins, and that is a spin inversion symmetry. And if you have got polymers, usually they also have sigma symmetry. That means you just flip them around, Okay, like you take a polyester chain and flip them around, you get back the same chain. So that's another thing. So you basically have four symmetry elements that's identity included E, P, J, and sigma, and of course their products. And all these things commute, so it's an abelian group. So when it's an abelian group, you have a eight one-dimensional representations in the group, the point group character table. Okay, so they are all written down here, the character table for a system as this. You can just write it by inspection. And what you do is you set up, you take the DMRG basis vectors and project from the basis vectors the symmetry adapted vectors. And the way to do the symmetry adapted vector projection is the following. I think I have written the. Okay, so the projection operator is very simply, the character times the operator, which is summed over the representations, and you take that and operate on the basis states, you get the symmetry adapted basis. You have to read out the linear independent states. So it's quite simple. One can do that using standard group theory, and you can get the energies of states which are, the ground state is always the AE plus representation, which is corresponding to the plus under electron hole symmetry, and even under this spin inversion, and the optically excited lowest state will be a PE minus phase, and so on and so forth. Okay, so and it's important to get these things, because if you have degeneracy, it is going to show you that near the degenerate states you can have quantum phase transitions. If you are looking at, for example, spin systems, and you are looking at sigma symmetry, then you will see that you will have a possibility of a transition from antiferromagnetic spin density wave state to non-spin density wave state, and that's what a bounded state in the single ground state you can have if A plus E and B plus 0 are degenerate, because you can see. You can see this is possible with using symmetries, and in fact they have used this in dealing with quantum phase transitions in skewed spin ladders, which I will not go into. And you want to check the DMR, because you can show that optical gap that you get from exact calculations for a 12-side problem is what I've given here. So U by T equal to 4.0, the optical gap is 1.278 from DMRG, exact is 1.287. As U by T increases, you see that the optical gap becomes much more in good agreement. So the DMRG calculations are better for strongly correlated systems. And here I show, just for fun, the lowest states for a
Sorry, I have a question. Why DMRT can get the lower energy state than the ED method?
this one second.
Now, why DMRT could get the lower energy value than the ED method? Because ED method gets the exact value, right?
ED method is exact, but I want to check the DMRG.
Yeah. That's I thought I think DMRT got the higher energy values than the ED method.
Correct,
usually.
because DMRG is the variation calculation.
Yeah.
Okay, so it always is a higher variation bound, but variation bound is only for the grounds, not for the excited state. So the gap cannot be guaranteed to be the lowest. Only the ground state energy, exact ground state energy is the lowest. Okay, but the gaps, the exact gaps cannot be guaranteed because you don't have a variation calculation for the excited. Okay, so here it shows you, for example, these are all the covalent states, and as U increases, the covalent states coalesce, and this becomes, the spin wave states when U by T becomes very large, and this becomes the Stoner excitations of the chain when U by T is very large. So this is one spin wave branch, this is the excited electronically excited spin delta. Now I'll come to finite DMRG. One of the problems with the ordinary infinite DMRG sequence is that the density matrix that you are constructing, like rho of P, is that of a 2p side system. But what you are targeting is an n side system. So you want rho of P to be the density matrix of the p side of the n side system, not of the 2p side system. For example, if my target is 100 sites, and when I look at my 4-side density matrix, 4-side density matrix was constructed from a 8-side problem and not from a 100-side problem. So what you want to make sure is that the 4-side density matrix is also a 100 constructed from the 100-side problem. So if you want to do that, then you have to go into doing a finite DMRG calculation. And the finite DMRG calculation requires sweeping. That is, when you reach the target size, let us say I want to do the 100-side calculation. When you reach the target size, then you stop it there, and then instead of let me go to the next one. So what you now do is you add one side that you had here, n by 2 to the left hand side, and take out one side from here and call it n by 2 plus 1 and n by 2 plus 2, so that the system becomes a following. You have a system with the left block which is n by 2 sides, and the right block is n by 2 minus 2 sides, and then you have two other sides are here. Using this, you can construct the density matrix of rho n plus 2 just as before. Oh, this should have been plus, I'm sorry. N by 2, yeah, this guy, n by 2, because my system size is n, not 2n. And you can continue this process until you get the left hand side is n minus 3 and the right hand side has only 3 base. And now you reverse the calculation by having a one-side density matrix here and then 2 here now. Then you go rather 2-side density matrix here and 2 sides here, and that's n minus 4 there. 3-side density matrix, 2 sides and n minus 5 there, and so forth. And you keep sweeping it back. Okay. So when you keep sweeping it back, then you finally reach this point. Okay. When you reach this point, you have actually constructed new density matrices on the right side instead of the 0th order density matrices that I have the first iterated density matrix on both sides. Now I can continue the same way up and down and keep refining my density matrices for different sizes with each sweep. So if I do this with each sweep, then I get more accurate density matrices, and you can get much better accuracies in the energy eigenvalues. Okay. Let me now try to I will try to give you an introduction to the DMRG and matrix product states. Of course, the experts will talk about it later on. So what I'm going to do is the following. That is, you consider that you have gone to the rightmost extreme in your density matrix calculation. So your system has n sides, and you want to express your eigen functions as the eigenfunctions of the density matrix of rho n minus 1 and the Fox state space of n. Fox states are the last side. So which means that psi n I can write it as a sum over density matrix eigenvector mu n minus 1, and then the states of the last string sigma n and mu n minus 1 sigma. So this is the way I can write on my eigenscheme. But I know that mu n minus 1, the way I have calculated it before, is made up of mu n minus 2 and sigma n minus 1. So there's a matrix which transforms mu n minus 2 and sigma n minus 1 direct product into density matrix eigenvectors mu n minus 1 through the matrix A n minus 2, mu n minus 1 with mu n minus 2 and sigma n minus 1. Okay. So using this, you see that you have now a n minus 2, another matrix A n minus 2. You can substitute this one in here for mu n minus 1. If you substitute it there, what do you get? You get psi n now is n minus 1 mu n minus 1 sigma n, and A n minus 2, mu n minus 1, mu n minus sigma n minus 1. Then the product of mu n minus 2, sigma n and sigma n minus 1. So now you see that I have to sum of mu n minus 1 sigma n and also mu n minus 2 sigma n minus 1. So I have got this product. Now this is a product of two matrices, right? I can do the same thing until cows come home. So mu n minus 2 can be replaced by mu n minus 3 and sigma n minus 2. And if you write it down, then you'll have a product of three matrices. And if you keep continuing like that, then you'll get a product of all these matrices, okay, with one vector on the left-hand side and one vector on the right-hand side. And the product of these matrices A2, A3, An minus 1, and then sigma 1 on the left and sigma n on the right. So now what you see is that my entire eigenstate that I had, which was psi, which was in terms of the density matrix eigenvectors, I'm now able to express it in terms of the Fock space states of the n-side system. That is, in terms of sigma 1, sigma 2 to sigma n. And the coefficient for a given sigma 1, sigma 2, sigma n, like up, down, whatever it is nothing but the appropriate matrix element corresponding to our different sigmas, but summed over all the density matrix eigenvectors, which are auxiliary variables. Okay? Because in general, this whole thing should be just some C sigma 1, sigma 2 to sigma n times C sigma 1, sigma 2, sigma n, right? That C sigma 1, sigma 2, etc. sigma n, I have broken up into a product of matrices. Okay? So that's the reason why it is a matrix product. Okay? So if I write down for the rotation of the matrix product, for example, if I'm looking at a matrix AP, it has a mu P is 1, is a column index or the row index, whatever you want to call. Is a row index here, and mu P minus 1 is another index, and sigma P is another index. See, earlier I had taken a product of mu P minus 1 and sigma P and said it is a column index. Now I can break it up into mu P minus 1 and sigma P, and I can write the AP matrix as mu P minus 1 on the left hand side, mu P on the right hand side, and sigma P on the right. So it's as if I have written my 2 by 2 matrix, which is 2 index matrix, into a tensor, which is a 3 component tensor. The 3 components are mu P minus 1, mu P, and sigma. Okay. Now, if I say that if I have a common line between AP and AP minus 1, then the common line I say is nothing but taking place over mu P. Okay, that is contraction of the two matrices, or the contraction of the two tensors. So this becomes sum over mu P, AP mu P minus 1 sigma P, and AP plus 1 mu P plus 1 mu P sigma P plus 1. Okay, so I have summed over mu P in these two cases. So what I get is sigma P and sigma P plus 1, and then the two things that I get here are mu P minus 1 and mu P plus 1. So this becomes actually a tensor of 4th rank, because I have just contracted two indices. I have product of two tensors, which was actually, we tried to check 6 indices, but then I have contracted over 2 of them. So I get tensor of the 4th rank. Because of that, I can write down my ground state in the DMRT as a matrix product. So I have sigma 1 and sigma n here, and then all these matrices A2 to An minus 1, operating upon sigma 1, sigma 2, sigma n. So if you give me the elements sigma 1, sigma 2, sigma n, then the product of these matrices is going to give me the coefficient for that particular state in the eigenstate. Okay, so that's all that I have done. So this is a matrix product representation, and sometimes the diagram is written in this fashion.
Just to make sure, so the first phase in the first diagram is special in that it has 2 sigmas in the subscript, right?
Yeah.
Okay.
So actually, it's written slightly differently as just a one component vector. You put a dummy index here and some of it.
Thank you.
Now, an example, very simple example of an MP matrix product state is the ground state of the AKLT model. AKLT model is a spin 1 antiferromagnetic chain. A spin 1 has to come from 2 electrons, right? In materials, you only have electrons, so spin 2, spin 1 half, and 2 of them give you spin. So I have the spin 1 here, there is an antiferromagnetic. The AKLT Hamiltonian is obtained by projecting any two spins using the projection operator P2, which projects out the spin 0 and the spin 1 state. So you get this Hamiltonian. Okay, this is a AKLT. Now, this can be written as a matrix product, state and natural. So the ground state of this one corresponds to a singlet between the B type of spins, A type of spins on one side and B type of spins on the other side. So if I have a cyclic boundary condition, this A will come and have a singlet bond to the other. So this is the AKLT ground state. This is the way it is written. This is the singlets between the two spins and spin 1, two neighboring spin 1 objects. So I have the ith singlet is between Pi, spin Pi on side I and spin Ai plus 1 on side I plus 1, and the singlet is always written in this fashion. And in this basis, I can write down the state, the matrix sigma I as 0, 1 by root 2, 1 by minus 1 by root 2, 0, where the row represents the spin of B and the column represents the spin of. Okay? And you can have a direct product of these matrices because ground state is nothing but a direct product of all these singlets. Okay, because you have all these singlets and you are having a direct product, and that can be written as a direct product of these matrices sigma A of B1, A2, B2, A3, etc. Sigma BL using cyclic boundary condition, and this is the ground state. Now what you can do is, when you have got two spin halves, you can construct a spin 1, because either you can have spin 1 or spin 0. If you construct a spin 1, you have a ms equal to 0, ms equal to 1, and ms equal to minus 1. The three states ms equal to 0, 1, and 1, 0, and minus 1 are just given by these matrices. Okay, 1, 0, 0, 0. Okay, 0, 0, 0, 1, and 0, 1 by root 2, 1 by root 2, and 0, where again the rows and columns correspond to the spin index of the type A and type C. And you see that using this, I can transform my state, which was just a product of the sigmas, by transforming each of the sigmas into the m's. Okay, that is the ms values of the spin ones. So which means all I'm doing is multiplying by this one. So if I multiply by these, then this is the ground state now. And the ground state is nothing but the trace of these products of matrices. And the trace is can be written now as just trace of these matrices. Sigma 1, sigma 2 to sigma n, where A sigma and sigma. Okay. So now the point is, can you generalize this matrix product to higher dimensions? That was one of the questions. So let's see whether it's possible. So look at the full Hilbert space. The full Hilbert space is too large. Okay, and when you are actually doing either DFT or any of these calculations like semi-empirical Hartree Fock or DFT or mean field or whatever, then you are working at this point. Okay, very small region. Then you have the area law states here, which are very smaller, much larger, but still smaller than the full Hilbert space. And the area law states are the ones that represent the low energy states of the country. Okay, so my interest is only this. And gapped ground states obey area law, and correlation functions follow exponential, because there is a gap in the excitation. Correlation functions follow exponential, and you can extend this area law, the states which obey the area law, using vectors, tensors in higher dimension. But before I go into it, I just want to tell you, the notation that one uses. So the notation, if it's a scalar, you just write a circle, no lines going out, no legs. If it's a vector, there is one leg corresponding to the component index I. If it's a matrix, you have two legs corresponding to the two indices I and j. If you have a tensor of rank n, like the coefficient of a sigma 1, sigma 2 to sigma n, then you have n legs, and when you take an inner product of 2, you are just summing over one of the legs, A dot B. When you multiply a matrix into a vector, then you are summing over one index, so you get this one, only one leg back. And here, when you multiply 2 matrices, you trace over one of the common legs, and you get 2 legs back. And so this is how we will usually do it.
Excuse me, so you have 3 more minutes.
Okay, let me see. Otherwise, I can continue afterwards. So, but I'll take about 5 minutes. Okay, so now you see that my eigenstate, or the representation of the eigenstate, is in terms of the coefficient, which is a tensor of the nth rank, because there are n legs, I1, I2, I n. And what you can actually do is break it up into a product of the tensors of this in 3 legs, okay, of this type, like what we did in the matrix product space, okay. And this one will obey the area law. It is easy to show that anytime you have a matrix product state, it obeys the area law. So Shalbach has shown it in his review. If you want to look at it, or also there are also videos of this one by Vidal and others. See that. And the number of matrices scales linearly with the dimension of the problem. Whereas here, the number of components doubles every time you add a side. Okay. So if you have 64 sides, this is a 64 like tensor, 2 to the power 64 components you have. Whereas if you add an extra side here, it only increases the number of matrices by 1. So you can also define all this by pictures, the inner product. So this is the MPS, and the inner product is just complex conjugated. This object does not have any free legs, which means it's a scalar. Okay, if you want to have an operator expectation value, put in the operator here, which has got 2 legs, and then you contract over the 2 legs of this tensor corresponding to that side, and you get the expectation value of spin density and so on and so forth. Similar thing you can do with the ladders if you want to find the correlation function. Now, when you want to go to 2 dimensions, then you can write down the 2-dimensional system as though it's a 1-dimensional system and introduce interactions between 1 and 8, 2 and 7, 3 and 4, and so forth. But the problem is, when you break it up, then you see that there are bonds between, for example, when I break it up here, okay, you see that, no, when I break it up here, because that's, I've got a 12-side problem, so I break it up here, then you see that on the left side, I've got bonds between 8 and 10, 7 and 10, or 8 and 9, and so on and so forth. Because of that, there is an entanglement. And so that entanglement is not removed, and so the area law is not obeyed. So if you want to have an area law obeying diagram, then you must have what are called projected entanglement, entangled phase, where the in the interior, the tensor is of rank 5. That is, you have the physical index, which is shown by the arrow, and the auxiliary variables are shown by the lines left, right, or top and bottom. So you can use this tensor networks to actually represent the states of a 2-dimensional problem. And if you want to calculate the eigenvalue problem you want to solve, you can construct for one particular matrix. You can start with a set of random matrices that you want, all of them identical, and you can get an effective Hamiltonian for only one side in terms of one matrix. So now that matrix has got, if it's a m by m matrix, you have got m squared unknowns. You can minimize this effective Hamiltonian expectation value with respect to these m squared components, and you can get m linear equations, solve them, and in which case you get the matrix. And the matrix now you shift on to replace all the other matrices by this matrix, go to the next side and do the same. So I take the eigenvalues, and there's one way of doing it, and another way of doing it is by a projection operator method and using Schroeder decomposition. But I'll talk about some things about projection operator and Schroeder decomposition when I talk about the time-dependent DMRG. Okay, so right now I want to stop here and take any questions here.
Thank you, Professor Ramasesha, for a very clear talk. So now, because we have to go to the other institute this afternoon, so let me just take a few questions. Any questions? Yeah, Shimoka-san, please.
Thank you for your nice talk. I have a question.
Yeah.
I think you mentioned about the difficulty to get the accurate value in the configuration function from the same block.
Yeah.
And then you mentioned, I think this is because of the entanglement, so I couldn't understand why.
Okay, yeah. See, when two sides are in the same block, then there's always a bond between them. And you are not broken. So it means that if they are far apart, then they are having an entanglement because of that. Because they have an entanglement, you cannot treat them separately. So you take the product and treat them. Okay. So when you take the product, you are not treating them separately, but you are treating them together, and then you dissolve.
But is a minimalization problem?
There's a problem with the fact that even in the one-dimensional state, within the block there is entanglement, and there's no entanglement between.
And is that like something?
Yeah.
Yeah.
Any other questions?
Hello?
What is the limitation of the tensor network?
Limitation. Well, I think they only go up to 2 dimensions, 3 dimensions. I think next week we got to start. Because, see, I have not worked with tensor networks. I think they have read them. I don't have first-hand experience. Here's another. Sorry, here's one more.
You mentioned the APL law, right?
Yeah.
So, and you also mentioned that for the lower energies, we are only interested in that section.
The lower energy states, gaps, and they obey the area law. Lower energy.
Yes, I missed what is the relevancy of that area law?
Oh, okay. Because area law means that the relevance in the following sense. Okay. So supposing you have got they obey area law, and your tensor networks also obey area law. So the area law obeying states can be expressed in terms of
Area law obeying states.
states. So if you have states which are obeying area law, okay, they can be represented by states which also obey area law, which is a tensor network. So the tensor network states obey the area law because calculate the entropy of any block. Okay, that only scales as before. The higher energy states are spread out in Hilbert space. So the correlations are longer range. If the correlations are longer range, then the area law is happening. Because your wave function is the system is seeping into the environment, and so the entropy is big.
So there is a question from the online participants. So Jyoti, could you unmute yourself and ask a question?
Yes, am I audible?
Yeah, you are.
Okay, I have a question from your initial slide where you have said that when you have enough large density, then you can truncate the matrix from L dimension to M dimension.
Yeah.
So my question is that how do you know that you have reached that safe enough large density where you can truncate it?
Yeah, okay, that's a good question. So what you do is the density the trace of the density matrix is always 1. Some of the diagonal values is 1. So you make sure that total the densities of the states that you retain, they add up to as close to 1 as possible. That is, they are different from 1 by 10 to the minus 12 or 10 to the minus 13. Okay, then in that case, you have retained sufficient number of states.
Okay. And how does this truncation process reflect on the accuracy of the solution of your problem?
Oh, you keep truncating such that you are, for example, you truncated M truncated 2m or m plus 2, m plus 5, m plus 10 like that.
Hmm.
See the convergence. If the states, the energies of the states are converging with the increasing values of m, it means that your flow, your m value is pretty accurate.
Okay. Okay. I have one more small question, that what do you mean by coordinate relaxation?
Coordinate means, like if you have a vector, okay, every component is called a coordinate.
Yeah.
For example, the x coordinate, the y coordinate, the z coordinate of a point. Similarly, if you have a multidimensional space, each of these components can be called coordinates.
No, no, I mean, my question is coordinate relaxation.
What you are doing is, in the ith equation, the coordinate that you are relaxing is only the ith coordinate or the ith component. So in the first equation, you relax the first component. Second equation, you relax the second component. The third equation, the third component, and so on. Okay, and when you relax all the components once, you have completed one iteration.
Okay. Thank you, sir.
There are some other questions, but because we are running up over the time, so let me stop here and this Professor Ramasesha.
You can send a question on email. Or,
Yeah.
In the next class.
yeah, next class.
Yeah. So let's thank so we'll wait for lunch and we should be back at the gate at 1:15. Okay. So please do come because we'll be resuming at ISCS at 2:30. Right? The class is start. So this will be by 1:15. So please have a quick lunch and then get back to the main gate. Main gate.